In the last video, we introduced the idea of a mole. Now we're going to figure out why do we use this really strange, really huge number. Why 6.022 times 10 to the 23rd? Well, the reason is that it was discovered that if we have this number of particles, this number of atoms or molecules, whatever it is that we're interested in, whatever it is that we're investigating, if we have 6.022 times 10 to the 23rd of that particle, of that material, the weight of that sample in grams is the same as the weight of a single one of those things in AMU, which, to put it even in even more useful terms, it's going to match what's on the periodic table. So if you remember, on the periodic table we said that carbon, for example, has a weight of 12 AMU, roughly. Like it was a teensy bit off of 12, but roughly speaking it was 12 AMU. So a single atom of carbon is 12 AMU. If you have a mole of carbon, if you have 6.022 times 10 to the 23rd carbon atoms, that sample will weigh 12 grams. And that might seem like okay, whoop-de-doo, who cares? That is actually really, really important. It's really crucial, because what this allows us to do is it allows us to connect the mass of a sample, which is something that is relatively easy to measure. It's pretty easy to measure the mass of a sample. It allows us to connect that relatively easy measurement to the number of particles in the sample, which is something that is very difficult to measure. You can't look at a sample of carbon and take out some tiny tweezers and count the number of carbon atoms. It's just not physically possible. But because we have this nice little conversion factor now, where we can convert from the number of moles to the number of particles, and because we have a nice little conversion factor where we know that whatever the mass is on the periodic table, that is the mass of 1 mole, it gives us a bridge, it gives us a pathway to go from the mass of something to the number of particles, which is a really, really important thing for us. So this mass that is on the periodic table, which up to now we have just been referring to it as the mass of a single atom, or the weighted average of all the atoms of that element, we're actually from this point forward going to refer to it as the molar mass, or the molecular weight. There's actually multiple different names for it that all mean the same thing. So molar mass, molecular weight, molar weight, formula weight, they're all different ways of saying the same thing. So from this point forward, that is what we're going to refer to the masses on the periodic table. They are and I believe I usually use the phrase molar mass. I think that's the one I use the most often. But just keep in mind that all 4 of these names here mean the same thing. So those masses on the periodic table are the mass of 1 mole of that atom. So the mass number for carbon is 12.01 AMU. That is the average, the weighted average of all the carbon atoms in existence that we are aware of anyway, on Earth here. The molar mass is the exact same number, just in grams per mole. It is the number of grams that 1 mole of that material would weigh. So again, this is going to be really, really useful for us, because it's going to provide a pathway from mass to number of molecules, if that's what we want, or sometimes we will just go ahead and stick with just the number of moles. Since moles and molecules are directly proportional, since this is just a larger number of those things, often we'll just stick with going to moles and not go all the way to molecules or atoms, but it does provide us a way to go back and forth between these things. So if we have the mass and we're trying to find the number of moles in a sample, we'll use the molar mass, which again comes from the periodic table. And then if we need to go between molecules and molecules or atoms and moles, then we will use Avogadro's number, which is the 6.022 times 10 to the 23rd. So there is no direct pathway. That's what this is saying here. We can't go directly from mass to molecules and atoms. We always have to go through moles first. So let's look at a few examples here. So we have, let's see, there's a few different examples here. So we'll go ahead and work through this one together. So it says calculate the amount of carbon in moles contained, not contained, in a 0.0265 gram pencil lead. And the lead there is in quotation marks because pencils don't actually have lead in them. It's carbon. So, if we have 0.0265 grams of carbon, and we want to know how many moles of carbon we have, we are going from here, the mass, to moles. And so the way to do that is with the molar mass from the periodic table. And if you remember from the a couple slides ago, the molar mass from the periodic table for carbon is 12.01 grams of carbon for every 1 mole. So again, that was from back here, 12.01 grams per mole. And so we've had to flip that here to get the grams to cancel out. That's perfectly fine. Remember, conversion factors, which the molar mass is a conversion factor, allows you to convert between moles and grams. We can flip those any way we need to get the units to cancel out correctly. So the grams here are going to cancel, leaving us with moles. And if we do that math, let's see, I get 3 sig figs, so that is going to be 0.00221 moles. So remember, the leading zeros do not count for sig figs. Okay. So that is the number of moles of lead, or of a carbon, pencil lead, so to speak, in a single pencil. Now, I would like you to try to work this one out on your own. So go ahead and pause the video, read through the question, and try to work out how many atoms of copper are in 3.1 grams of a penny. So we're making the assumption here that we have pure copper, which is not a great assumption, but we kind of have to make that assumption. So assume the whole penny is copper. Alright, I hope you paused the video there and tried to work that out on your own. This one is a little bit more complex than the last one, because now, actually, I should have the 0 at the end there. Now we are going all the way from mass to atoms. So instead of just going from mass to moles, we're going to add in one extra step and go to the number of atoms. So to do that, this first step is the same as before. So we need the molar mass of copper, which I am going to need to look up real quick. I do not have that memorized. I want to say it's 60 something, but I could be wrong. Yeah, 63.55. So there are 63.55 grams of copper in every 1 mole of copper. And again, I got that from the periodic table. So I just went to the periodic table, I found copper, it's element number 29, and its mass number is 63.55. So 63.55 grams for every 1 mole. But that's not where I want to stop. I want to know how many atoms there are. So, I know that 1 mole of copper is 6.022 times 10 to the 23rd atoms of copper. And that one I don't have to go and look up a special number because this is true for everything. 1 mole of anything is 6.022 times 10 to the 23rd of that thing. So if I check my units here, grams cancel, moles cancel, leaving me with atoms. And if I do that math, 3.1 divided by 63.55 times 6.022 times 10 to the 23rd. Let's see, I get 3 sig figs, so 2.94 times 10 to the 22 atoms of copper. So a pretty big number, but once again, we're talking about atoms here. They're infinitesimally small. And so to make up a penny, which is, relative to our size, is not all that small, it's going to take a lot of atoms to make that. All right, let's move on to molecules here. So with molecules, it's the exact same process as atoms, except now we have more than one atom involved. So in the previous two examples, we just had carbon, or we just had copper. Now we have examples where there are multiple elements in the molecule together. So if we're trying to find the molar mass of sodium hydroxide, for example here, all we have to do to find the molar mass of the molecule is add up the individual molar masses. So we're going to go to the periodic table, find sodium. Sodium is 22.99. And all of these are going to be grams per mole, but I'm going to leave the unit out for now and add it in at the end. So 22.99, that's the sodium. Oxygen, depending on which one you look at, it's either exactly 16 or it's 15.9994. I'm just going to go with 16.00. And then hydrogen is again, depending on which periodic table you look at, it's either 1.008 or 1.01. I'm going to go ahead and go with the 1.008. It's a slightly more precise. So if I add all those together, I get, and let's see, I get 4 sig figs, so I don't get to keep all of these. And actually, with 4 sig figs, that's going to end up being exactly 40. So when you add all those together, you get 39.998. But since we only get to keep down to the hundredths place here, because again, the rules are slightly different with addition. Since we're adding these together, we can only keep to the last common decimal place. And so that would be the hundredths place. And so we would round up 39.998 to exactly 40. So 40.00 grams per mole. That is the molar mass of sodium hydroxide. Okay, so that next question there, what is the mass of 3.4 moles of sodium hydroxide? Well, we know the mass of 1 mole now. 1 mole weighs 40 grams. So if we have 3.4 moles, and we know that every 1 mole weighs 40 grams, our moles here cancel out. That is going to be 136, oops, ran out of space there, 136 grams. So then the last question here on this top part, how many molecules are in 1 gram? Well, we can do that here. If we have 1 gram of sodium hydroxide, we want to know how many molecules there are. We are going to be going from here, a mass of 1 gram, to here, the number of molecules. So we're going to have to go to moles first, and then use Avogadro's number. So if we do that, again we have 40 grams for every 1 mole. And then Avogadro's number tells us that for every 1 mole, we will have 6.022 times 10 to the 23rd molecules, in this case. Sorry, when I try to write really small, my little writing pad here gets upset with me. Sorry for making that look really nasty, but that is molecules there. And so if I do my math, 1 gram divided by 40 times 6.022 times 10 to the 23rd gives me 1.5, and let's see, I get 3 sig figs. So 1.51 times 10 to the 22 molecules of sodium hydroxide. All right. So we worked through that top one together. Why don't you go ahead and give the bottom section here a shot on your own. A couple words of caution here. Remember that when we have parentheses like this, the subscript outside the parentheses applies to everything inside the parentheses, but it will not apply to the calcium here, since the calcium is outside the parentheses. And then remember here that we have kilograms. The molar mass on the periodic table is in grams per mole, so you will have to convert this kilograms. So keep that in mind as you pause the video and try to work through these 3 questions on your own. When you come back, we'll work through them together. Alright, I hope you paused the video and tried to work those out. Let's look at the molar mass of calcium nitrate. So calcium has a molar mass of 40.08. Nitrogen has a molar mass of 14.01, and we have 2 of them. So we're going to have 2 times 14.01, and I believe I'm out of space to write here, so we're going to add the oxygen down below here. So we have 6 oxygens. Each of them are 16 grams per mole. So we have 40.08 plus 2 times 14.01 plus 6 times 16. And if we add all of those together, we are going to end up with, and I guess I'll put it right down here. So it's going to be 164.1. And I guess, yeah, so we would get one more 0 there. 164. Oh, wait. Did I do that right? No, yeah, I did that right. Okay. Sorry, questioning my calculator work, but I believe I did that correctly. 164.10 grams per mole. Okay. So that is the molar mass of calcium nitrate. The next question was, what is the mass of a billion molecules? It's a billion molecules. It must be a big mass, right? Well, let's find out. So if we have, and I'm going to go ahead and give myself 2 sig figs here. Actually, I'll give myself 3. So we have 3 sig figs there, 1.00 times 10 to the 9 molecules. Because a billion is 10 to the 9. If I want to know the mass of that, I'm going to be going in the opposite direction, essentially, what we've done up to this point. I'm starting here with molecules, and I'm going in this direction. I'm going to moles, and then to mass. So the first thing I need to do is I need to divide by Avogadro's number, because that will give me the number of moles. And then I'm going to multiply by the molar mass, because that will cancel out my number of moles and leave me with a unit of grams, which is what I want. So again here, molecules are going to cancel, moles cancel, leaving me with mass in grams. So 1 times 10 to the 9 divided by 6.022 times 10 to the 23rd multiplied by 164.1, the billion molecules only weighs 2.73 times 10 to the negative 13 grams, which is really, really tiny. A billion molecules, even with a relatively large molecule compared to what we've seen up to this point, is still very, very tiny. Very tiny. Because molecules are very, very tiny. It takes a lot more than a billion molecules to be able to work with that material. I don't think you would even be able to see that sample. I think that would be too small to see. And if you could see it, you'd have to have just the light just right. It would be very, very difficult to see that for sure. Alright, so then the last one here, how many moles are in 5 kilograms of that material? So if we have 5 kilograms, the first thing we need to do is we need to convert it out of kilograms, because our molar masses work with grams. So if you remember, 1 kilogram is the same as 1,000 grams. So that first conversion factor gets us out of kilograms into grams. And now we can use the molar mass. So we have 164.1 grams for every mole. Notice now that we're dividing by the 164. When we multiplied before, it's because we're going in the opposite direction. So in the previous question we were going this direction, but now we're going back this direction. We're going from mass to moles. And so we're flipping the conversion factor in order to do that. So my kilograms here cancel, grams cancel, leaving me with moles. And if I do that math, so I have 5 times 1,000, which is just going to be 5,000, divided by 164.1. So that is 30 point, let's see, I only get 2 sig figs. Oh, bummer. So actually with proper sig figs, that would be 3.0 times 10 to the 1 moles. If you had 3 sig figs, it'd be 30.5. Ran out of space to write there, but it'd be 30.5 is what that would be if there were 3 sig figs. Alright. I think we'll call it there for this video. Did quite a few example problems in this video, which is a good thing. Example problems are always good. In the next video, we're going to talk a little bit about percent composition, which is a topic that every once in a while is very important, and sometimes it's not quite as important, but it is something that you need to understand and know how to calculate. So we will talk about that next time. I'll see you then.